You didn't quite read the terms and conditions.
All right, terms and conditions, I like that, that's a good way to start. Okay, what am I doing?
There's on a different planet, at
Okay.
the surface of the planet,
Okay,
with negligible friction.
okay.
There is a toad in a bucket attached to a pulley.
A toad
In a bucket.
in a bucket, all right.
Attached to
So
a pole.
there's my bucket, and, hang on, that's a toad. Shh.
So the pulley unwinds and lands on the spring.
Okay, so wait, so there's, there's something like this, right?
Yeah.
And is the strings either wrapped around the pulley or like coming up from,
Yeah.
okay. And then, so we got motion this way, and then there's a spring down here, okay?
So when it lands on the spring compresses, and you want to find how far the spring compresses.
Okay, so, so the spring is gonna squish, and that's sort of my, the question that I'm trying to find. Right?
Yeah.
Okay, and we're saying negligible friction,
Yeah.
which means,
Ignore the friction.
yeah, okay, so,
Yes.
what do I know about the pulley?
You know the radius of the pulley.
Okay, and is it constructed of a like uniform material? Can I assume basically that it's like a disc?
Yes.
Okay, do I know its mass, or can I'll just say that its mass is m, does that seem reasonable?
Yes.
Okay, so this will be MP, and then this we'll say is MB for bucket and bullfrog together. Is it a bullfrog? It should be a bullfrog, so that I can use the same letter. I'm just gonna say it's a bullfrog, all right? This is a bullfrog. That's a command decision. All right, so this is a super problem. There's a few different things that we have to think about here. The first is that largely you will have all the tools that you need to solve this problem. Is it starting from rest?
Yes.
Okay, so we know things like we're gonna have, in this case, conservation of mechanical energy. So there's no kinetic energy, but if there was, that would be one of our starting conditions. Gravitational potential energy, elastic potential energy. Those are our three forms of mechanical energy. And that is gonna equal some later kinetic energy, some later gravitational potential energy, some later elastic potential energy. And there will also be some maybe thermal energy that's produced, and we've got something else to think about here. So you said there's negligible friction, right?
Yes.
And so as this unwinds, we're not losing any of our energy to friction. We're gonna say there's no air resistance, there's no friction. So I'm gonna throw something out and then we'll come back to it. So what I'm gonna throw out is, you all can imagine if this pulley were basically like massless, then this object would be in free fall, essentially. And if it's in free fall, it's gonna land and it's gonna squish the spring a certain amount. Let's start adding mass to this pulley and let this, it's a disc, right? So it's uniform. Make it more and more and more and more massive until it's so massive that as this thing unwinds, it just accelerates at just a fraction of the free fall rate. And then when it lands on the spring, it's only gonna squish a little bit. Our initial energy is all stored in the form of gravitational potential energy. Our final energy, so far as we know, is gonna be stored in the form of elastic potential energy in the spring and there's still gonna be some gravitational potential energy relative to the ground. We can deal with that in a couple of ways. So we could say that there's gonna be some gravitational potential energy. There's not gonna be any kinetic energy, but here's the problem. I just outlined two scenarios in which the elastic potential energy is dramatically less, right? If this thing is moving real fast right before it hits the spring, then the spring's gonna compress a lot more. If it's moving really slowly, then the spring is gonna compress a lot less. Is it reasonable to think that the change in elevation is gonna make up for that? Like it's gonna be a little bit higher up off the ground, is that gonna make up for it? Well, not necessarily, because the change in elevation is potentially gonna be minuscule, right? Like if we have a spring that is designed so that a tiny little change in its position results in a huge change in the amount of elastic potential energy stored, then the difference in height might be a millimeter. But we're gonna still see like a lot more energy stored in one case in the spring than in the other one. Not gonna see a tremendous difference in gravitational potential energy if this thing ends up a little bit higher in one case than it would in another case. So where is that energy going? We'll come back to that, okay? The part that you do know is, first of all, we can say, just to kind of simplify things, we can say that our zero height, our location of zero gravitational potential energy in this system is the lowest point that this bucket is going to occupy. Doesn't have to be the ground, doesn't have to be relative to the ground. This is on a different planet, but even on a different planet we could dig a hole and things would fall down. So it's sort of arbitrary to have it be the level of the ground to begin with. So let's say that our h equals 0 is our zero gravitational potential energy. So that means our final gravitational potential energy is going to be 0, which means so far as we know right now, there's no thermal energy that's produced. There's no kinetic energy or elastic potential energy to start with. So what we have is something that looks like this. Our gravitational potential energy should be equal to the elastic potential energy. What do we need to know for our gravitational potential energy? We need to know the change in height. We need to know the mass of the bullfrog in the bucket. And we need to know G. But it's not 9.8 meters per second squared because we're on another planet. So if this planet has like if we know the mass and we know the radius of the planet, then we could figure out G for this planet based on that information, the same way that we figured out G for Earth, or that I guess Professor Dave figured out G for Earth, and I sort of showed you a slide that had it. But we can find this with enough information, or we could just leave it as a variable, and then we could say, well, this is going to depend on what planet you're on. It's going to depend on the density of the planet, and how far away you are from the center of the planet. But we can deal with that. But we would need to have some information. One thing we could do to find G, if we really wanted to, is we could just drop something and then measure its rate of acceleration, right? Like if I were to take the frog and say, okay, don't jump, man, just like let yourself fall and put like a nice little soft pillow underneath it so that the frog falls onto a pillow. But if we've got our little frog and we just drop it from rest, then we can measure the displacement and the change in time. We have an initial velocity of 0 and a constant acceleration from a constant force, which will be true provided the planet is big enough. Then our acceleration is going to be 2 times the displacement divided by time squared, and that's free fall. So that's going to tell us what G is for this planet. So we could do that if we really needed to figure it out, or we could figure it out by using the stuff about the planet, the mass and the radius of the planet. Let's table that for a second, okay? Because this, we know we could figure this out somehow. We know the mass of the bucket. We assume we know how high up off the ground it is. And that's going to be equal to our elastic potential energy. And our elastic potential energy, we've talked about the idea that it is 1/2 times the force the spring exerts at a certain compression times the distance of that compression. So that's going to be 1/2 times the force that we measure at the compression times the distance that it's compressed, all right? And this is really what we're looking for here. What's the force going to be, by the way? Anybody have any idea? We know what the force is. Aaron?
How fast it's going in free fall now. Oh.
We know what the,
the mass of the object times the.
Yeah, so in equilibrium, we could put our frog, so if you're talking about the maximum compression of the spring, right? Yeah, so that's gonna come at the moment that the frog isn't moving. So we couldn't use that because at that moment, we're not in equilibrium. The moment that the frog isn't moving, the frog is actually accelerating upward. Time out for a second. Does that make sense? How does that make sense? I'm telling you that if you jump onto a spring, here's you jump onto like a platform that's held up by springs, you're gonna land on the platform, and then you're gonna go down, and the platform is gonna squish. And there is gonna be a moment where your velocity is 0, and your acceleration is upward. What does that mean? Yeah.
It means that as you're going down, you actually had velocity, but when you started compressing on the spring, the force you exert into the spring is now starting to exert upwards into you, which is canceling out your velocity, and then you start.
The force you exert on the spring is being exerted upward into you, which is canceling out your velocity. I think I know where you're going with that. It's not quite like that though, right? Because the force you're exerting on the spring is always going to be equal and opposite to the force that the spring exerts on you. The instant you touch it, that's true. Because that's Newton's third law. So the whole time that you're in contact with the spring, the force it exerts on you is the same as the force you exert on it. No matter what, that's the case. When I take this spring and I put something on it, the force between the spring and this board are the same. As I squish the spring, that force is increasing, but it's still the same. The spring is pushing up on the board with the same force that the board is pushing down on the spring. It's still true, it's still true, it's still true, it's still true. Even when the spring is all the way squished, now I'm just pushing, right? It's not squishing anymore, I'm just increasing the force. The force between the spring and the board is still the same. So this is getting weirder and weirder and weirder. What's happening here is that when you land on that spring and you squish it, the force from you on the spring is always the same as the force from the spring on you. But that force changes relative to your weight. If you were to look at your weight over time, what you would see is it looks like this. If you were to look at the force from the spring pushing up on you over time, what you would see is this. At this moment, right here, you are instantaneously in equilibrium. Your acceleration is 0, but you're still moving down. Past this point, the force from the spring on you up is greater than the force of gravity on you down. And the force of the spring continues to grow and continues to grow and continues to grow. It continues to grow till your velocity is 0. And at that point, a free body diagram would show that the force of the spring is many times greater than your weight. There's a net upward acceleration. Your velocity is 0, but you are experiencing a net upward force from the spring when it's at its maximum compression. That's why you start moving up. if the acceleration were 0 right here, if the acceleration were 0 and your velocity were 0, you would stop. That's not what happens. When you squish a spring from elevation, you land on it and it squishes and then pushes you back up like a trampoline. So with our frog, that's going to happen here as well. But we can still figure out a whole bunch about the spring by using the frog's weight. Okay? So what I would say is, take the bucket with the frog in it, put it on the spring. Just put it there. And let the spring compress until the whole system is at rest. At that point, the velocity is 0. More important, the acceleration is 0. At that point, the upward force from the spring, the downward force from gravity on the frog in the bucket are going to be equal and opposite. At that point, we can use the weight of the bucket and the frog in it to determine the upward force of the spring. We can use that in conjunction with the change in displacement to figure out how hard that spring is going to push at any displacement. It's linear, remember? So if we look at a graph like this, this is the force from the spring, this is the compression distance, we might find that our equilibrium point is right here. Okay? This is where the upward force from the spring is equal to the weight of the frog. We can figure out what the distance is. At that point, we can figure out how much force will be exerted by the spring at any distance. Okay, it's going to be whatever the equation for this line is times the distance itself, right? The force is always going to equal the slope of this line times the distance. We didn't get into this too much. You talked about it a little bit with Mr. Ayer. And it's come up a couple of times in class, but basically what we can do, if we measure force on a spring and the displacement of that spring and divide those two things, we get what's called the spring constant, which is how much force you get for a certain amount of compression. And that spring constant is usually, we usually use the variable K. And it turns out that if we know K, then the elastic potential energy of a string or of a spring is kx squared, because kx is going to give us the force. Kx times x is x squared. So essentially what that means is we don't have to know in advance how far the spring is going to squish in order to find the amount of force that is going to be exerting at that point so that we can use this equation. We can find the spring constant instead. Just squish it. Figure out how much force, figure out how far we squished it, divide those two numbers, and now what we're looking for is this variable right here. It's squared, so we're going to have to take a square root, but we don't need to measure two different variables at the same time, right? Whereas here we would have needed another force and the squish of the spring. Okay, so that's one of those arenas where, okay, that's more than what I would have expected you all to come up with because we didn't talk about this specifically, but it's there. This piece, you should have recognized G isn't going to be 10 because we're not on Earth. Ideally, you would have been able to come up with a couple different ways of thinking about what G is. You could use this. You could use Newton's universal law of gravitation. And so now we've got something that's really, really close, right? Like we've got the gravitational potential energy, which now we know we can figure out something about, and we're looking for elastic potential energy at the end to be the same, and we know we can find K, so all we need to do is find X, but now we're back looking at that conundrum of, but wait a second, the pulley has something to do with this, because if this pulley is big and really difficult to rotate, in other words, if it has a large moment of inertia, then the frog in the bucket is going to be going slower. And if it's going slower, then it's going to take less time to reach its velocity of 0, which means the spring is going to be squished less. So something can't be right about this. If energy is conserved and nothing is lost to friction, And we start with only gravitational potential energy, and we end with only elastic potential energy. Somehow, we're not taking the pulley into account. So, what's the solution? Does anybody have any thoughts? Like, where is the extra energy? Johnny, what do you think?
So most of the energy would be going into the rotational acceleration of the pulley.
It goes into the pulley, doesn't it? We know about momentum. Momentum tells us how hard something is to stop. You could imagine that we could think about, we talked about linear momentum, right? Like if something is coming toward you and it's very light and or it's going really slowly, you just kind of stop it, right? But the bigger it is and or the faster it's going, the more difficult it is to stop it. We also talked about kinetic energy. And kinetic energy had to do with those same two things, only instead of thinking about how hard something is to stop, we thought about how fast could something that's moving make something else go. We can do the same thing with angular quantities. Angular momentum has to do with how hard something is to stop. So how many of you have done ceramics at all ever? Okay, so you know the wheel, right? It's big and it's heavy. If you have that wheel going, and especially if it's the old school like manual ones, and you want to stop it, do you just kind of like put your elbow on it? It's really hard to stop those things. They have like a big cement block. They have a lot of rotational mass. They have a big moment of inertia. They have a lot of angular momentum. It's really difficult to get them to stop. Now imagine that instead of getting them to stop, you're using them to make something speed up. So let's say you've got your wheel spinning around and around and around, and let's say it has a little paddle on it. And so this is spinning around with the wheel, right? Like if you were looking down at the top, it would be going around in circles like this, right? And then if we were to put something in front of that, it would hit it. The faster that wheel is going, the faster it's going to be able to speed something up that it hits. That's energy. If something can speed something up, it has energy. The faster it goes, the more energy it has. The more massive it is, the more energy it has. With angular motion, it's not just how fast it's going and how massive it is, but it's where that mass is located. If we were to take our plastic wands, if I were to take the red one and spin it around in a circle and then put something in front of it, that red one would hit something and it would go blip, blip, blip. The blue one with the mass out toward the end of the wand would hit that same thing and make it go a lot farther. It has more energy because it has a larger moment of inertia. Our extra energy is rotational or angular kinetic energy. And it turns out we have an equation for that. At the start of this thing's motion, there's no energy stored in rotational motion. At the end, there is going to be kinetic energy and stored in the rotation of that disk. And it turns out angular kinetic energy is equal to 1/2 I omega squared. It's just like kinetic energy, 1/2 mv squared. For linear objects, it depends on the mass and the velocity. For rotating objects, it depends on the rotational mass and the rotational velocity. 1/2 moment of inertia times omega squared is going to give us joules. That's where the extra energy goes. So that's why I was asking, is the disk, is the pulley a solid uniform disk? Because if it is, then the moment of inertia of a disk is 1/2 mr squared. We know the mass, we know r. We can find 1/2 mr squared. We can either measure the rotation of this and use angular kinematics to figure out its final angular velocity, or we could measure the linear distance of the frog in the bucket and time that to find its final linear velocity. Either way, we can figure out what the final angular velocity is. That is going to be what allows us to determine our second piece of energy storage at the end. We're gonna have energy stored here. The more energy storage we have here, the less we're gonna have here, right? So you make this pulley have a larger moment of inertia, and if it's uniform, the only way we can do that is by making the mass, but it's gotta have more mass, right? So if it's made out of plastic, frog in the bucket goes down, lands quick, like moving pretty quickly by the end, and you get that spring squished a lot. If it's made out of concrete, much less, there's much less squish at the end. Either way, all of the energy that's not stored in the spring is gonna be stored in the rotation of the pulley at the moment of contact, okay? Yeah,
Is it okay if I make like a small mini like addendum problem, like just to go along with this?
sure, yeah.
At what point is the kinetic energy at its max?
So
Like the rotational kinetic energy.
it'll be, so the bucket and the rotational kinetic energy are gonna be at their max right before you hit the spring. So this is simplistic, because what this is gonna allow us to do, and we're running out of time, which is why I didn't bring this up, but what this is gonna allow us to do is find the kinetic energy, the frog in the bucket right before it hits the spring. And at that point, what's gonna happen, and so we don't know what happens to this pulley, okay? I was sort of assuming that once the frog starts to slow down, the pulley's just gonna keep spinning, right? Like it's just gonna keep unwinding, because what would stop it? So we're still gonna have that angular kinetic energy stored in the pulley. This will reach its maximum right as the frog hits the top of the spring, and then it should stay constant. The frog's kinetic energy is gonna start dropping as the spring slows it down. So the maximum total kinetic energy, rotational and linear, is gonna be right as that frog hits the top of the spring. If something slows the pulley down, so that when, like if this were a cable, like a really stiff metal cable that could pull and push at the same time, then when the frog comes to a rest, so will this. And in that case, a bunch of the energy that was in the rotation of the pulley is gonna be stored in thermal energy, right? It's essentially an inelastic collision that's going on between the cable and the pulley, and we're gonna lose a bunch of our energy. It's gonna be stored as heat, right? As this whole system comes to a halt. So it sort of depends on what that cable is like. Now, if the cable is totally inflexible, then all of the angular kinetic energy in the pulley will be put back into you'd end up at the same distance, right? Basically, if this ends up being a conservative system for storing energy, then it might as well not even be here. The frog is gonna squish down the same distance, whether it's in free fall or whether it's supported by a pulley. In one case, its own kinetic energy will be transferred to the spring. In the other case, the angular kinetic energy will be transferred to the spring through work done by the bucket and the frog in it. So it can get kind of weird depending on what's connecting the pulley to the bucket. But if it's just like a rope, then this is gonna land on the spring and this is just gonna keep spinning. That energy isn't gonna go anywhere, still stored in angular kinetic energy in the rotating pulley system. Yeah, so that's a great problem, and I mean, we kind of got our way through it, I think, for the most part.